Sometimes some forces are invisible, but they play a key role in our life. Like it may be love, it may be gravitation. You can see it, but you can feel it. And some poet write on love, like love is like this much beautiful, can be compared to this flower, can be compared to this beauty of nature. Just like this, physics make us to compare gravitational field with some lines, electric field with some lines, which we call it gravitational field lines, electrical field lines. So when suppose a mass is attracting, we represent some lines to show that it is actually attracting the body towards itself. If some charge is repelling, we feel it like it is repelling towards this direction. If it is placed here, we'll push it towards this direction. If it is placed here, and a mass will attract towards this direction if it is placed here. Basically, we use these electric field lines or gravitational field lines to represent how this field actually is directed. Although these are our man-made thoughts, and we can say that these lines are not actually present. These are just our fiction that we draw wind like this symbol. But do actually wind look like this? No, obviously no. These are all our convention to understand the topic. So if I draw a sphere just enclosing this mass, these field lines will actually look like just passing through that sphere, because just assume that this sphere is massless. This is just our imaginary sphere, a hollow sphere of our imagination. Then it looks like this field line is actually passing through the surface of this sphere, right? Actually the field lines are also along all the direction, means you can say that 360 degree is covered by some field lines. I am unable to represent this the field lines going inwards in this direction or the field lines behind it, because obviously this is a 2D board, I can't represent it three-dimensionally. So it is your responsibility to be creative and imagine these things. So basically some lines will pass through the surface. So we want to actually calculate the amount of lines passing through the surface. So if some lines, here the line is perpendicular to the surface as the line is passing through the center. But if the line was something like this, then this is not perpendicular to the surface. So basically, if it is making an angle theta with the area vector of the surface, then we can say that this is E dot ds. The field dot the surface vector will be equals to the flux. The new word is flux. So actually the amount, the intensity of the field perpendicular to the surface is known as flux. Here the field lines are helpful to imagine this thing, although this thing is not required in our calculation, but to just understand the topic I have drawn the field lines and showing you that if this is a surface, I take a small element of this is the area vector, the field is making an angle theta with it, then the flux will be E dot ds, means E, the component of the field along the direction of the normal vector to the surface. We draw area vector normally perpendicular to the surface. You know that the direction of the area vector is perpendicular to the surface. Therefore, E dot ds will give us the component along the direction of the component of the field, component of the intensity of the field along the direction of the area vector, or you can say perpendicular to the surface. So here is E dot ds. We know about electrostatics. In electrostatics there is a Gauss law, and which helps us to find the flux. We say that flux is equals to E dot ds, closed integral, which means that if a surface is a closed surface is enclosing some charge, then the flux is equals to charge by epsilon naught, a constant. So just like this, to calculate flux due to some mass enclosing the flux due to this mass, we can draw a Gaussian surface, and after drawing the Gaussian surface, we can simply say that this flux will also be equals to E dot ds, obviously the normal formula, and after applying Gauss theorem, it will be equals to minus 4 pi g into the mass enclosed by 8. Simply you can compare it with electrostatics. Closed, you know that the surface should be closed for this formula to be applied. So here the electrostatic field dot ds was equals to q by epsilon naught, the charge enclosed by the Gaussian surface by epsilon naught. Here the constant is minus 4 pi g into mass. You can say that the mass, the sign of the constant is negative, which indicates that the flux is actually inverse. You know that we have two things, a source and sink. If the thing is source, means the flux is outward. It means it will have a outward flux. And if the point is a sink, the flux will be inward. You know that you might have seen that from the source, from sun, light is going outward. Yes, light is traveling outward and into a sink, like suppose a black hole, the light is going inward. You can say that sun is a source and black hole is a sink. So now we are clear about this. We can use this Gaussian theorem, Gauss theorem in many cases of like that of our solid sphere, spherical shell and all, to know about its flux. Its actually if we know the mass and all, we can calculate the flux, and if we are able to calculate the flux, we can use these two equations to derive the field due to that mass. So I hope you know about Gaussian surface. Actually this is an imaginary surface, just like the spherical shell I drawn here for the mass. This mass I have drawn here a spherical shell. Actually due to symmetry, we be able to solve this calculation for spherical shell or solid sphere. But in case if the thing is unsymmetrical, or yes, if the thing is unsymmetrical, then it is a little bit difficult to calculate the field, because simply you are here using I will show you the example. The calculations be like, okay, the field is same everywhere, so I can calculate the point, means I can divide the area and tell that at this point the field will be equal to this, because if I say for a surface area the total intensity is E, then for a point it will be equals to E by easy. But if this is not symmetric, something like this suppose, and I create a Gaussian surface something like this, then here the point is a little bit more distant than that of this point. Here the distance is less between the Gaussian surface and the mass, but here is more. Although my drawing is a little bit wrong, that's why it looks the same. But imagine, let me draw another picture. Here the distance is small, but here it is large. So you can say that the field will be equal at this point and this point, and because there is no symmetry in this picture, we can just simply divide the electric field by the surface area. But in case of this, all the points lie at same distance from the sphere, so you can simply divide electric field by the surface area. So let us take a case of solid sphere. For outside point, we are going to calculate electric field into ds equals to minus 4 pi gm. So here we know that the mass is m. Let us suppose capital M. Then we can say that E dot ds. I am taking a Gaussian surface here at a distance smaller from the center of the solid sphere. Then E into the surface area of the Gaussian surface will be 4 pi smaller square, which is equals to minus 4 pi g into capital M. From here, actually after closure integration, the electric field will be same at every point of the Gaussian surface. So integrating the ds, I will get the surface area, which is equal to 4 pi r square. And now if I cancel 4 pi, I will get electric field to be equal to minus gm by smaller square, which was found by the usual method in previous classes. And something like this you can also find it for the point on the surface, where small r will be replaced with the capital R. And for a point inside, we can say that E into ds will obviously be 4 pi small r square. Here is the point is to find the mass, 4 pi g into mass. Mass will be equal to volume into its density. Volume will be 4 by 3 pi small r cube. Density will be mass by 4 by 3 pi capital R cube. So 4 by 3 will cancel out. R square will cancel the R cube, and we will be left with 4 pi cancel. Electric field to be equals to minus of g m by capital R cube into small r. Obviously the same equation. And for the spherical shell, simply inside there is no mass, so Gaussian surface will enclose zero mass, and if here the mass will be equal to 0, the field will be equal to 0. And for outside point, the same case. And for the point on the surface, just replace the small r with capital and you will get your answer. So now we are going to derive Poisson's equation. So now we are going to talk about Gauss divergence theorem. We have talked about Gauss gravitation theorem on gravitation, and actually the Gauss divergence theorem is a topic of mathematical physics which is really very useful to solve critical crucial problems, because it has to change the nature of the integration. Means if you are doing a surface integration, you can change it to a volume integration and vice versa by using Gauss divergence theorem. So basically it states that the closed surface integration of a field is equals to integration of divergence of the field, the volume integration of divergence of field. Basically this thing is Gauss divergence theorem. So, surface integration, closed surface integration of the field is equals to volume integration of the divergence of the field. Here actually for volume you can put triple integral, and for surface double, but simply you can also write something like this to represent Gauss divergence here. So now we are going to derive actually Poisson's equation. So we know that curl of E vector will be equals to 0 because electric field is a conservative field and curl of a conservative field is equals to 0. I guess you know about properties of conservative fields. If you don't know, simply this is one of the property of the conservative field. So, and we also know that field vector is negative of gradient. So from the previous Gauss theorem on gravitation, we found that electric field is equals to minus 4 pi electric field into ds, yes, equal to 4 pi gm. You can write it as minus 4 pi g dm, integral of minus 4 pi g dm, because we are simply here integrating mass and will find the total mass. Mass is equals to volume into density, so you can write density into, let us consider a small volume of the mass and it to be d tau. So now we have minus 4 pi g tau being equal to this, and we can say that yes, this is the another point, E vector equals to this thing. And here, as we have used d tau for volume, we can also say it to be volume integral of divergence of E vector multiplied with d tau. And from this equation we see that left hand side is same, so we can say right hand side to be equal. So now we are left with a divergence of field vector equals to minus of 4 pi 0 d tau. I can take it to right hand side and we will be left with divergence of electric field plus 4 pi 0 whole integral of with respect to the integral of the total thing with respect to d tau, means the elemental volume. So after if this thing will be equal to 0, obviously the differentiation of the thing will also be equal to 0, and we will simply say that yes, divergence of E vector plus 4 pi 0 to be equals to 0. So now you can simply say that divergence of field vector equals to minus 4 pi 0, and if I take divergence of electric field equals to minus 4 pi 0, and I know that electric field equals to negative of potential, yes, negative of potential. So I can say that divergence of negative of gradient of potential is equals to minus 4 pi 0. Here I can say that Laplacian means double derivative of potential, you can also say so, not double derivative but something like similar to it. Laplacian of potential is equals to 4 pi 0. Here negative sign will cancel out, therefore Laplacian of potential is 4 pi 0. And if I take the form in coordinate system, the Cartesian coordinate system, I will get d2v by dx square plus d2v by dy square. Let me write here because it is our end result, d2xy d2vy dx square plus d2vy dy square plus d2vy dz square equals to minus 4 pi g rho. This is the Poisson's equation. This is for today. Thanks for watching.